Hello everyone. So in the previous classes, we discussed about the shift registers and the ring counter and Johnson counter. So since now we'll be discussing in length about the different counter operations and basics. So today's topic is counters. My name is Shiv Charan Puri, Assistant Professor, EC Department, Asansol Uni College. Now what's a counter? Counter is one of the most useful subsystem in a digital system. Counter is a sequential circuit that is used to counting the number of clock pulses arriving at its clock input. So this is in essence. That's counter is basically used to count the number of clock pulses. A counter is a set of flip-flop connected in cascade. The flip-flops are interconnected such that their combined state at any time is the binary equivalent of the total number of pulses that have occurred up to that time. Thus, as its name implies, a counter is used to count pulses. A counter can also be used as a frequency divider. If we have n flip-flop, the input frequency is divided by 2n. They are also used to perform the timing function as in digital watches to create time delays, to produce non-sequential binary counts, to generate pulse trends, and to act as a frequency counter, etc. So we know that primarily sequential circuit, if classified based on the application of clock, is broadly of two types. Okay, that is synchronous counter and asynchronous counter. Synchronous counter and asynchronous counter. Now we will focus on asynchronous counter. So in asynchronous counter, the external clock pulse is applied to the first flip-flop, and the output of first flip-flop, either Q or Q, whatever, is connected as clock of the next flip-flop. So that is actually the asynchronous operation. That is, one output is actually the clock of the successive flip-flop. Similarly, each successive flip-flop is clocked by the Q or Q bar of the previous one. Therefore, all the flip-flops do not change state at the same time because they are not triggered simultaneously. There is some propagation delay between responses of successive flip-flops. The asynchronous counter is also called as ripple counter. Why? The term ripple counter comes from the mode in which the clock information ripples through the counter from one flip-flop to next. Okay. Let's now talk of synchronous counter. In a synchronous counter, all the flip-flops in the counter change state at the same time in synchronism with the clock input clock signal. So that means they are synchronized with the same clock. The clock signal in this case is simultaneously applied to the clock inputs of all flip-flops. Since all the flip-flops are clocked together, the delay time is less. In synchronous counters, whether the flip-flop toggles or not depends on the flip-flop inputs J, K or D or T or S, R. Hence there is need to be additional logic circuitry to ensure that the various flip-flop toggles at the same time. Okay. So let's discuss a 4-bit synchronous up counter. Considering the counting sequence of a 4-bit binary count shown in table below, as you can see here, it's a 4-bit synchronous up counting. It will start from 0000, then 0001, that means 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so on. Okay. Flip-flop 0, you can see here, toggles with every clock pulse, as you can see here. You can see here, flip-flop 0 toggles at every clock pulse. Flip-flop 1, you can see here, toggles only when the output of flip-flop 0 is in 1. Okay. One state. Flip-flop 2 toggles only with those clock pulses that the output of flip-flop 0 and flip-flop 1 are both at logic 1 state. And flip-flop 3 toggles only with those clock pulses when Q0, Q1 and Q2 are all in the logic 1 state. This logic can be easily implemented with AND gate as shown in figure below. We will discuss. This is a 4-bit synchronous counter using JK flip-flop. The timing diagram or waveforms are just shown in the self-explanatory. So as you can see here, this is a 4-bit synchronous counter. You can see here it is driven with the same clock. Okay, and simply using AND gates we can obtain this. As you can see here, this is a 4-bit synchronous up counter operation. Now coming to asynchronous counter operation. A binary ripple counter consists of a series connection of flip-flops in toggle mode, with the output of each flip-flop connected to the clock input of the next higher order flip-flop. Since flip-flops are used in toggle mode, we can construct counters using JK flip-flop with the J and K input tied together from T flip-flop. Another possibility is to use a D flip-flop with the complement output connected to the D input. In this way, the D input is always the complement of the present state, and the next clock pulse will cause the flip-flop to toggle. So it's not like that you cannot use D flip-flop. You have to use D flip-flop in a specific configuration. Also, we may use positive edge triggered or negative edge triggered flip-flop to design counters. For simplicity, all counters using negative edge triggered JK flip-flop is considered. So let's discuss about the 2-bit ripple up counter. The 2-bit up counter counts in the order 0, 1, 2, 3, then 0, 1, 2, 3 and so on. Or in binary as 0, 0, 0, 1, 1, 0, 1, 1, then again 0, 0, 0, 1 and so on and so forth, etc. A 2-bit ripple up counter using negative edge triggered JK flip-flops is shown in the figure below for simplicity. The timing diagram is also illustrated. As you can see here, there is a simple 2-bit ripple counter. This is a timing diagram. Okay. As you can see here, when there is a no clock pulse, it is 0, 0. Okay. When there is a first clock pulse, suppose here there is a first triggering up, a negative edge trigger happened here. Let us talk of this Q0. Then as previously there was 0 over here. So with this first clock, what will happen? This all JK are connected to 1. So this will always toggle. Okay. So what will happen that here after this first clock pulse, this 0 will now change to 1. Okay. But here what will happen? In this Q0, 0 becomes 1. Okay. So 1 will reach here, but as it is negative edge triggered, nothing will happen, so it will remain the same. You can see here, if it is 1, it remains, it is the previous state. Okay. And also you can see here, see, it is Q1 Q0. So Q1 Q0 0 0, Q1 Q0 0 1. Okay. So you can see here, it is changing state. Okay. But this Q1 is not changing any state as such. And in this way, at every stage, it will count from 0 0, 0 1, 1 0, 1 1. So that means it will be a 2-bit operation. What other up counting? Counting sequence of a 2-bit ripple up counter. As you can see here, as I told you, in the first clock there will be nothing. In second clock, Q0 will be set to 1, or rather it will be toggled to 1 actually. But here, as there is a negative triggering, because of this 1 there will be nothing, and so there will be no state change. Okay, and likewise you can repeat for other clock also. 3-bit ripple down counter. So now let us see a configuration where now you will be down counting. For ripple counters, the flip-flop used must be in toggle mode, as we have discussed. The T flip-flop must be used in toggle mode by connecting T input to the logic 1. It is the most simplest, we require only one input. The flip-flop used to construct the counters are negative as triggered. The clock inputs are fed from Q outputs. The counter counts in the reverse or downward count sequence. So the logic diagram of a 3-bit down counter using negative edge trigger T flip-flop are as shown below. As you can see here, it's a simple T flip-flop. Okay, and this is the connection. So now let us see the counting sequence. In the first clock pulse, as you can see here, order 1. So that is the demand. That for down counting, we require that previously all the flip-flops should be preset to 1. Okay. Then the first clock pulse, what will happen? Same. This should be 0. Now see here. With this first clock pulse, what will happen? Now, previously everything was 1 over here. Okay. So what will happen? This becomes 0. This becomes 0. Okay. And now, if this becomes 0, this becomes 1. If this becomes 1, there will be no change here. This clock is basically not triggering because here is 1. It will only trigger on 0. That is what we mean by negative edge triggering. So it will retain the previous state. Okay. So that means the next with the first clock, the output will be 0, 0, 1. Then with the second clock, the output will be 0, 1, 0, then 0, 1, 1, then 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay. We will see. You see. So it requires 8 clock pulse. Okay. So 3-bit down counter. Thank you.